Okay, in the last video, I was trying to get the system on chip, the processing system running on this Zynq-7000. Really, the primary purpose for me going down that path was to try to get a clock over to the programmable logic. So from the processing system to the programmable logic, but that requires that you would have that processing system running. The reason I was doing that is the only usable oscillator I have on here so far is an input going into that processing system. So my goal was to see if I could use that, generate the appropriate clock for the programmable logic so that I could then drive an LED or something like that. Now, I did comment that I've got a temporary 25 megahertz on here, which may be causing issues. It looks like you need a minimum of 30. I do have that part on order and should receive it this week. And I had used the 25 because I had failed to order the 33 back when I ordered all the parts for this project. And I wasn't patient to wait, and that's fine, but that's a 25 on there still. Now, if I don't have that clock, then I need to figure out how do I get a clock to the programmable logic or the FPGA side of this. And you have to go through certain pins on the FPGA, clock capable pins, clock input capable pins. And I did not set up an oscillator anywhere on this to go into one of those pins. So my expectation has been to go through the processing system and then drive all the clocks from that. And I don't have any clocks straight into the programmable logic. So I had to solve that. And how I solved that is what you see here for my testing. So got a good old-fashioned CAN oscillator up here. It's just a simple 1 megahertz just to test this out. And I grabbed one of these little cards that I had built in a previous project, and it just takes a bunch of signals from the other side of this, connector. And it was for a different FPGA project, but then it brings them over into these 7 headers, which formats it in a PMOD format. So if I got a bunch of different PMOD devices, I can just plug them in and work with them from that other FPGA project I was working on. Well, unfortunately, when I built this board, I completely changed the layout of the pins. So there's 68 pins here, and I went from one structure I was using or one setup on the previous project where this was used to a different one. So I did have to pull some pins, and you're going to notice on this connector here maybe that it's missing some pins up front, and there's a couple throughout, and then more down here on the bottom. So top and bottom, and 2 sections in the middle that I pulled. I just physically pulled the pins before I soldered in this connector. And I did that to make sure that I don't accidentally run any signals in those pins, which then go to power or grounds over here. I didn't want to short any pins out. So I took out any pins that could potentially cause me issues, and then that left, another, 50 some signals that I can work with, which is plenty, as long as I have access to a clock input, so a clock capable input over here on one of these headers. So that's what I did. I tracked that down. So which one of these pins goes to a clock capable input, and that's a pin over here. So what I'm doing up here is running an oscillator. I'm pulling power for the little breadboard off of this header up here. So in these headers, I do, supply a 3.3 volt and a ground on the edge over here. So I grabbed the 3.3 volt and the ground, took it to the breadboard. Then I run that 3.3 volt into the oscillator, out of the oscillator through a resistor, then a jumper over to this. That'll give an input into the FPGA. And then I also wanted to be able to drive something on the output to see if that works. So I, again, found a signal I wanted to use, found which pin that's going to, grabbed that, run it through a resistor LED to ground. So I know this is not ideal. I've got it's only a 1 megahertz oscillator, so that's probably not a real big deal as far as noise and stuff. And actually, I put the scope on this, and it looks fine. My grounding is a concern. All the grounding it's basically going from the FPGA out to the LED, through the breadboard, back up to this ground up here to get back to the FPGA. So that's a pretty big loop. Same thing on the clock input. Clock is coming in through here, but the ground is coming back up through this up here. But that's what it is for this test, I guess. I think that's it for this setup. So it's basically I'm providing an oscillator, and that oscillator is giving me a 1 megahertz clock coming into an appropriate pin to take it in as a clock, and then using it and have a little bit of Verilog to then flash an LED. So right now I have this powered up. I've got the programmer powered up, but I actually need to program this because I had just turned power on to all of this. So over here on my computer, let me walk through what I have. I'll start with this constraint file. I did change the resolution of this screen. I dropped it down just so things wouldn't be so small in the video. So hopefully this is easier to read. There's a URL here that I did go out, that's got all the pin information for this specific Zynq-7000 I've got. But then I configure my clock. And so I create a clock. I call it CLK. Period is 1000, which I believe is correct for a 1 megahertz oscillator. I then tell it that it's on pin Y6, which is one of these MRCC pins, which is basically a clock input type of pin. And I tell it that it's a 3.3 volt. And then I have my LED, and this is the actual, basically the output signal on this pin here, which happens to be Y11. So I just say, okay, I want to call it LED on Y11, and I also want it to be a 3.3 volt. So that's my constraint file. Then I went up to some code here. I found a simple little example that I quickly just adapted. So it takes in my input clock, it sends out the LED. I'm setting up a parameter for how fast, so 500,000. So this loop is going to go until essentially that number is met as it counts. And if I got a 1 megahertz oscillator, that means at half a second it should flip my LED. And then half a second later, it'll flip it the other way. So half a second on, half a second off, half a second on, etc. And then this is just doing the counting. When it gets to that threshold, flips my LED, resets the count, and off we go. And if it's not at that number, it just keeps counting. And so it counts until it gets to the number. Half a second later, flips the LED on or off, goes another half a second, flips it the other way, and just repeats that. So I went through all that, I generated the bit stream, and now I'll just go ahead and see if I can connect to the board. And so let's see if I can get connected to my Xilinx platform cable USB 2 here. I hear it detecting it in Windows. Okay, so that looks like that detected it fine. So I'm going to go ahead and do a program device. And this is my bitstream file. And I'll go ahead and do a program. When it gets done programming, I should see my program or my done light up here, which is this light right here. And I should see my LED flashing over here if that's all working. So program's done. That LED is flashing just fine. If I want, maybe I want to speed it up. So let's just say, and I probably could do a couple things. Obviously, I could put a faster oscillator in. So that'd be one thing to do here. But I could do a couple of tests, I guess. Maybe I'll grab, if I want to, for the fun of it, try a different oscillator, I can grab one. Oh, let's just say I've got a little drawer of miscellaneous oscillators here. And I have a 10 megahertz here that I'm not even going to turn this off. What could go wrong, right? So I'm going to pull this oscillator out and put in this 10. And now you can see that LED is flashing more rapidly. So 10 megahertz, not a problem. I don't know how fast I can go before this little setup will fall apart, but I'll just leave that 10 in for now. So now maybe I go back to my code just to see if I can reprogram this. And I suppose I want to slow it down now. So let me slow it down. Oh, maybe I'll have it be, if I add a 0 here, that's going to make it 10 times slower. So take me back to that, what I had for speed before. And maybe I'll even slow it down even more than that. So I'll put a 10 here. So that should be, half of the original speed I had, I believe. So let me save this, and I will just go ahead and do a generate bit stream. And in the upper right, I can see it's running the synth design. And this will probably take a few minutes at least. Maybe while it's working through that, I guess it seems like, the programmable logic here is all working fine. I'm providing just about, the output of this little box is a little over 5 volts. By the time it gets through the cable and gets to the input, it's about 5 or just shy of 5 volts coming in here. Again, then I'm pulling the 3 volt up here for all of this. And, this LED is doing its thing just fine. And I can see I'm pulling 80 milliamps roughly. Again, this thing isn't very accurate, but it's in the right ballpark probably. Let's see. Initializing design. Now, another suggestion I had from the previous video was, maybe get in and try to get, some type of terminal output coming out of the sock so that I can connect, Teraterm or something like that and send some text to that. I believe Phil's lab, that's what he does as one of the early tests when he does his Zynq-7000 bring up video. He uses that. So I'll definitely do that. Now, for me to do that, though, I have some components down here that I need to get loaded up, I believe. So I've got this FT2232 down here and all the components that will need to be connected, the little USB connector, and then see if all of that works. And so that's some learning I've got to do yet when I get to that. So I didn't want to jump to that right away. I was just using this header up here for doing my programming and debugging, this JTAG header. Okay, it looks like as I was talking there, my bit stream completed. So let me go ahead and program device. But now that got done, and you can see that this LED is flashing at that slower pace, and this is even with that 10 megahertz oscillator in there. So I think that's all good. So that gives me, a little more confidence that parts of this Zynq-7000 are working. And again, next steps is I need to get the proper oscillator. I'll see what that does as far as the processing system. And then after that, I'll probably try to configure the RAM and maybe build a much simpler test setup for it than I had in the last video. But that's a test of the programmable logic and my very, very simple test, taking in an oscillator and feeding out an LED signal. Blinking LED seems to be going okay.